Hello and welcome. My name is Taylor Rault, and this video will discuss how some aspect of mechanical engineering is affecting climate change. Now, it is fairly common knowledge that greenhouse gases are a significant contributor to climate change, as they trap thermal energy in the atmosphere, causing a rise in temperature. It is fairly simple logic that in order to reduce the amount of greenhouse gases that we produce, we need to reduce the amount of fuel that we consume and burn. For my case, I'm discussing the transportation industry and how fuel consumption can be reduced there. Fuel is essentially stored energy, so in order to use less of it, we either need to increase our efficiency or reduce our consumption. Now we have cars, which have most often internal combustion engines, and bikes, which have manpower. So in an internal combustion engine, we have roughly 30% efficiency, and in a car we have a mechanical drivetrain, so we have roughly 75% mechanical efficiency. This is due to often torque converters, which you lose energy there due to slippage, and you also have just losses due to poor lubrication. Now, you can do simple math and say 0.3 times 0.75 is equal to 22.5% efficiency. This brings us to the bike, which has roughly 25% muscle efficiency, which is converting food into energy. And we have roughly 95% mechanical efficiency. Now, this is pretty high, and in the ideal case on a bike, you can actually have up to 99%. But this is not the ideal case. There might be a little bit of dirt in the chain or not optimally lubricated. So 0.25 times 0.95 is equal to 23.8%. And due to these being roughly the same in magnitude, we can't really conclude too much from that. They're roughly equal in efficiency. This brings us to aerodynamics, where we have our drag force formula. You can see right here. And so we have, in a car, large frontal area, a low coefficient of drag, and very high speed. And since speed is squared, it's a very, very large contributor to the formula, and to the magnitude of the drag force. Now, in a bike, we have a relatively low frontal area, but a high coefficient of drag due to the lack of the optimal shape when you're riding a bike, and low speed compared to a car, so this is very low. From these factors, and the density of air being equal for all cases, we have a fairly large drag force for a car, whereas we have a small drag force for the bike. Therefore, we can say that the bike is the better choice. This brings us to rolling resistance. From the free body diagram, you can get this formula, which is your rolling resistance force, which is required to pull something against a resistance, which is equal to your normal force times your coefficient of rolling resistance. Now, this coefficient has many factors that influence its magnitude, but the biggest of which is just deformation of both your surface and your cylinder on which you're trying to roll. So, in a car we have a very high normal force, however a lower coefficient of rolling resistance than that of a bike. In a bike we have a very low normal force. This brings us to saying that the rolling resistance force for a car is much greater than that of a bike. Therefore, again, we can say that the bike is better. This brings us to energy use, which is a culmination of all these factors. So for a car traveling at 100 kilometers an hour, it takes roughly 20 kilowatts or 27 horsepower to maintain that speed. And to travel 100 kilometers at that speed, it takes 1 hour. And so from our formula, which equates power and work, we have power times time equals work. So therefore we have energy use is 20 kilowatt hours for traveling at 100 kilometers an hour for 100 kilometers. Now for a bike, we have, for traveling at 15 kilometers an hour, we have roughly 60 watts of power use, which is very reasonable output, because think about riding at 15 kilometers an hour, you're not really working too hard. Now this, for 100 kilometers an hour, takes 6.7 hours, and so again, doing the simple multiplication, we have 0.4 kilowatt hours of energy use to travel 100 kilometers. Therefore, we can say that the bike is much, much more efficient in this regard. It makes sense that a car uses a lot more power at higher speed because drag force is proportional to speed squared. However, a bike rider going at 40 kilometers per hour will only use roughly 300 watts. So if you scale that up, it works out that the bike is still actually more efficient. And this is only for constant speed. So if we consider accelerating and decelerating a very large mass like a car versus a smaller mass like a bike, it takes much more energy, as kinetic energy is equal to 1/2 mv squared. So if you have a very large mass, you're going to take a lot more energy. Therefore, the bike is much more efficient. As a result, we can see that the bike will produce fewer greenhouse gases and will therefore be better for the environment and have a smaller impact on climate change.